All right, so this video is going to be support for the homework for Chapter 9. And I'm going to start us off here by going over and reviewing kind of how we create hypotheses for these hypothesis tests. So there's two hypotheses that you are going to be creating here. One is going to be the null hypothesis. Okay, and the null hypothesis, which we note as HO, okay, here, is going to be the current situation or current standard, okay, or the current claim. H1, which can also be written as HA, okay, is our alternative hypothesis. And this is what we are trying to prove. Using data. So usually what happens here is we have some current standard or a claim that is being made, and we're under the assumption that everything follows either the Z distribution if, let's write this actually, Z distribution if sigma is known, or the T distribution for means if S is what is known. Okay. And then you want to see, like, I'm going to go out, I'm going to collect some data, so you'll have some sample size here. And based on that data, let's just use means for now. Based on that sample data, do I have enough evidence to say that HA is actually what is going on instead of what we think should be true? Okay, and so then you're going to have these bounds here. So if you want to be a certain level of confidence, like let's say we want to be 95% confident in our answer, so then we would choose a significance level of 0.05, and then depending on the tail of your hypotheses, okay, that might be a left-tailed test, that might be a right-tailed test, or it might be a two-tailed test. And what we say is, like, if your X bar is far enough away from your null hypothesis, then you have significant evidence in favor of the alternative. And so the first set of questions that I want to do in this video are like how to write these hypotheses. And I'm going to put the book here underneath the document camera so that you can see this. So let me just transition things a little quickly here. Okay, and so we're going to look at this question here, 9.8. I'm going to move it up in this corner so that I can now write my responses. Okay. All right. So on part A, it says, what if we want to test the mean amount of time spent watching sports on television by adult men and see if that's different than 9.5 hours. So my null hypothesis is that the mean amount is 9.5 hours. And then since it says is different from, then my alternative hypothesis is just not equals to, which means this is going to be a two-tailed test. Okay, versus something like C, to test whether the mean starting salary of college graduates is higher than $47,000 a year. So I would say, okay, well, the center of my distribution, where I'm going to set my HO, is 47,000. And then I want to test, hey, do I have significant evidence that it's actually higher? So H1 would be that mu is actually higher. So in this case, I'm only testing the one side. So I'm going to have a one-sided test, and we're going to call it a right-tailed test. okay, because I'm testing the right-hand side of the distribution. And so hopefully that's helpful in setting up a lot of these hypotheses here, which we're going to be doing throughout the video, but I just want to make sure that you had some basis here before we jump into some of the other sections and problems here. All right, moving into section 9.2. Again, I'm going to just transition a few things here. All right. In section 9.2, I want us to look at problem 916, which is just kind of that first basic question to look at. Okay, and it says, show the rejection regions for the following. And so let's go ahead and look at this here. Okay, and I want to show you kind of how to use your T-chart strategically in order to answer these questions. Okay, so here on 916, it says find the rejection region, assuming under the normal distribution, for a two-tailed test, alpha equals 0.05 and n equals 40. Okay, so under this assumption here, I'm not really going to worry right now about the sample size, because I know that right now that sigma is known for these problems. And so I can actually just use the z distribution. Now, when you did inverse normal questions, you would go to your z distribution and try to figure out, right, where the probabilities all are in this z distribution right here. But what I want to show you is actually if you go to your t distribution in the book, so page B21, okay, here, but if you go to the back side, okay, and these are all right-tailed. We'll talk about this in just a second, okay? But if you go to the back side of the t distribution where it says continued, go all the way down to the infinity row, this is your z distribution here. Okay, so it actually already finds all of these for you. You don't have to go look in the z table. It's at the bottom of your t distribution table. And that's basically is saying, like, if I know sigma, then sample size doesn't matter, and I can just assume that I have a z distribution, so I can just use that degrees of freedom being infinite here. Now, another thing, if you have a two-tailed test, you need to break up this alpha to be on either side. So we want to make sure that I have 5% broken on both sides. So when I'm looking actually under my right tail here, I'm looking in this column all the way down, and I get 1.96. So my critical value would be 1.96 and then negative 1.96. Anything in this shaded region we would reject in favor of the alternative hypothesis. We would have significant evidence that we have a difference from what we are currently claiming. Anything inside the non-shaded region, okay, then we assume nothing is going on. Let's look maybe at part B, okay? On part B here, they want us to do a left-tailed test with alpha equal to 0.01, okay? Now, you can still use that distribution table at the very bottom with infinite degrees of freedom, even though it's a right-tailed, okay? Because you have that symmetric distribution, so it doesn't really matter. I'm just gonna turn that critical value into a negative. So if you look under your 1 here, all the way down, okay? I'm going to use this value here. I'm just going to make it negative. So negative 2.326. Okay, and then I will leave C up to you, kind of using those new tools here. All right, looking also at some questions here in 9.2. We go back here. All right, let's look at 9.28. So I'm going to go ahead and get us set up here. So on 9.28, it says a telephone company claims that the mean duration of all long distance phone calls made by its residential customers is 10 minutes. Okay, so that's their claim. Their claim is that the average long distance phone call is 10 minutes. Okay. And then it goes on to say a random sample of 100 long distance calls are made by residential customers, and we took records and they show that the mean duration of calls is 9.2 minutes. And the population standard deviation is known to be 3.8. And all that tells me is I can do a z-test here using the z-distribution, okay? Part A says find the p-value for the test of the mean, okay, to see if it is different from 10 minutes. So I was waiting here to make my alternative until it told me just different from. So we're gonna run a two-tailed test here. How we're going to do that is, let's draw a little picture. Now remember, HO is my middle, so 10 is my middle. And in this question, it wants us to use an alpha level of 0.02. Okay, and then I'll show you how to find the p-value and the range and all of those things, and how to use your calculator as well. Okay, and give you some help on that. All right, so our z we would calculate by doing 9.2 minus 10 all over standard deviation square root of n. Right? And so if we plug that into our calculator, we get a z-score of negative 2.105. Okay, and so this x bar is 2.5 standard deviations, or not 2.5, but 2.1 standard deviations below the mean. Our big question is that far enough away from 10 to say that there's significant evidence that the mean calls are different from 10? So if you go to your probability chart here and you would just go to your z chart, okay, negative 2.10, well, let's round that. Let's make this negative 2.11, okay, would be 0.017. But remember, we're running a two-tailed test, so I do have to consider that on both sides here. Okay, and so my overall p-value is that times 2. So my p-value for this situation is 0.348. Okay, now what we are going to look at is we're going to say, like, is this p-value greater than or less than my significance level right here? And that p-value is too big. It is greater than the alpha level. So we're going to conclude fail to reject based on the p-value method. The other way that you could look at this is the critical value method. Now again, since we're looking at the z distribution and I'm looking at a two-tailed test, I can look on my t-table all the way at the bottom, okay, and my critical value would be 0.01 on each side. Right? If I take that alpha and I split it, I'd have 0.01. So that z for my critical value, if I'm looking here and go has to be 2.326 or larger. 2.326 or larger is my critical value, plus or minus 2.326. And so then I could evaluate here. I could say my z at negative 2.11, right, is not further away from 10 than my critical value. It is smaller than my critical value. Which would lead us to that exact same, rejection region right there. Okay, now this is how you would do it in your calculator. So if you go over to stat and you go over to tests, okay, we're running a z-test here and we have the statistics. That's what we're going to be plugging in. Our mu naught, that's your HO, okay, is 10. Our standard deviation is 3.8. Our mean is 9.2 and our n is 100. We're running not equal to. You can say calculate or draw, and draw is kind of fun because it will, I think I have something in my y equals. Okay, but draw is fun because it will go through and actually draw the distribution, the normal distribution, and then shade your two sides in, and then you can kind of check your paper and be like, oh yeah, that is what it looks like, okay? And then you can see, we use the table, so we're a little bit off, okay, in our calculation here, but that's okay. Okay, we would reach the same conclusion here, which would be fail to reject. Now let's look in the next section. Let's look and see what happens when we have to use the t-distribution, because that can make things a little bit more tricky here. So specifically looking at question 9.38, okay, in that question, they give you that you're looking at a null hypothesis that mu is equal to 100, and then it says we have a sample of 35, okay, and then you're wanting to find the critical values or the rejection and non-rejection regions for an alpha of 0.01. And then in part A, it says under this alternative hypothesis, so the mu is not equal to 100. So in that case, I'm going to have a two-tailed test. Now, I do not know the population standard deviation. I'm using the sample standard deviation as an approximation here, and so because of that, I have to be running these under the t-distribution, just like we did for confidence intervals. Where that makes that tricky is I then need to know the degrees of freedom, which is n minus 1. All right, so if I'm looking at an alpha of 0.01, but I'm looking at a two-tailed test, I'm going to divide up that alpha value on either side of my distribution here. And then when I'm looking under my t-distribution, I'm not going to look all the way down. I'm going to look at degrees of freedom being 34, which is actually here on this first page. All right, so my right tail here is 0.005, and then I go all the way down to 34 degrees of freedom, and I get 2.728. So my critical value here is plus or minus 2.728. And I'm going to go ahead and shade in that rejection region here. Okay, I'm going to leave B and C to you. It's only one-tailed test, so you don't have to split up your area for your alpha, but that's how you would use the t-distribution table to help you answer those questions. Let's look at an actual test here. All right, so let's look at question 944. So 9.44. All right. Let's see, I'm going to look this up in the book real quick and show it under the document camera because it is a word problem, so I wanted us to look at it together in this video. Okay, so this is kind of how we're going to dissect these questions here. Okay, according to Value Penguin, the average annual cost of automobile insurance was $1,388 in the state of Nevada in 2014. An insurance broker is interested to find if the current mean annual rate of automobile insurance is actually now more than that. Okay, so let's think about this. The current or the standard that we are comparing to would be $1,388. Okay, and then the insurance broker is looking at, is it actually higher than that? I keep hitting this cord here, y'all, sorry. Okay, she took a random sample of 100 insured automobiles, and she found in that sample that we have a sample mean of 1413 and the sample standard deviation is 112. Okay. Part A wants us to use the critical value method under an alpha level of 0.01 in order to figure out if the rates are now higher. Okay, so if I have an alpha level of 0.01, but I have a right-tailed test, all of that 0.01 goes over here. Now 1388 is my middle. Okay, so let's look at our t distribution here. Now, n of 100, which is why I wanted to do this one, on your t distribution, you only go to 75 here in the book. So we're just going to drop it down as if we're in the infinite here, and then here's my column that I'm looking at. I mean 2.3, and then we're off by 100th, so I'm not that worried about it, but I'm going to say, okay, my critical value then is 2.326. So if my t is greater than that value, then I can reject. So let's calculate t for this situation. And I'm also going to show you how to run this in the calculator. So t would be 1413 minus 1388 all over s over the square root of n. And when you put this in the calculator, you end up getting 2.05. Now, 2.05 is not bigger than this, because if our rejection region is here at 2.3, okay, 2.05 ends up being right here. Okay, so I'm going to say fail to reject. And then on part B, it says, hey, go find the range for that t value. So the range for this t value, 2.05, would be somewhere between 1.96 and 2.326, which means my p value then would be somewhere between 0.025 and 0.01. So if I wanted to change my alpha level maybe to like 0.05, then I could reject and I'd be in the rejection region. But at this case, I'm not. Okay, so and then let's do calculator talk here. So if you want to look in your calculator, okay, this is how we're going to do this problem here. So you're going to go under stat, test, and you're going to run a t-test because you know S, not sigma. You know the statistics. You're going to plug in everything. We're doing a right-tailed test, so you want to change that, and let's click draw. Again, I like this feature on the 84 that it does. I don't know if the 83 does this, but this one does. Okay, so you can see our t-value here, we did that correctly, and then it finds the p-value exactly for you, not just the range, but it finds the exact p-value for you. So under R alpha, that p-value is too big, okay? It would not be significant evidence of greater than, but if I wanted to change my alpha level, okay, then we could maybe get some significant evidence here. On the last section, okay, I want us to look at question 9.62, and this will be our last question that we look at here. And we're now looking at proportions. We're in section 9.4, and so we're looking at qualitative data, and can we do these things still with qualitative data? And the answer is absolutely. You just have to change it to proportions, okay? And so when I'm looking at this question that I want to pull up here and then put it under the doc cam for us to look at, okay? Okay, it says, according to the U.S. Census Bureau in 2014, 62% of Americans 18 and older are married. A recent sample of 2,000 Americans age 18 and older showed that 58% of them are married. Can you reject the null hypothesis at a 1% significance level in favor of an alternative that it's actually now lower than 62? All right, so let's use this to create our hypotheses. So the standard that I'm comparing this to is 62%, and I'm going to use P and not mu, because mu, okay, is for means, meaning we have quantitative data, okay? P we're going to use as for proportions, okay? And I'm trying to say, hey, is this proportion really less than 62% now? Okay. It tells me to use an alpha level of 0.01. The sample size is 2,000. And the sample proportion that is given is 58%. Now I want to know what is that as an actual value, like what is the X value under that? Now remember, X over N gives me 0.58, so I can just multiply 2,000 by 0.58 to get 1160, okay? And that's all the information that we really need here. And it says in the problem to use the critical value approach and the p-value approach. So we will do that, okay? All right, so let's go ahead and draw in our distribution here. So our distribution would be centered at 0.62. And our Z is going to be calculated the following way. Okay, we'll do 0.58 minus 0.62 all over, and then we got to use the sampling distribution, standard deviation here. All right. We get negative 3.62. Oh, that seems very, very far away. Okay, so let's do the critical value approach first, and then we'll do the p-value approach. So under this alpha, and I'm doing just a left side test, right? Let's see what that critical value would be. So I'm going to open up my t-table and go to the very bottom under infinite degrees of freedom. And I'm looking at 0.01, and it's 2.326, so it must be negative 2.326. If I have a z-score, okay, that is further away from 0.62 than my critical value, then I reject. Z is definitely further away than my critical value. I reject HO. Okay, so that's one way that we could solve this. The other way is using the p-value. Now, what makes this kind of tricky is you have to convert this kind of to the right-hand side, okay? And 3.6 isn't even on here. So all that I know as far as the p-value is concerned is that p must be less than 0.001. Okay, and I'm getting that because this is 3.1 essentially. I'm looking for 3.6. So 3.6 would be over here if that existed. And so I just go up here and say, okay, well then my p-value must be less than whatever this indicator is here in my table in the top. That p-value is very low, lower than my significance level. Conclusion is the same. Now, how do we do this in the 84? Okay, so you're going to go under that stat and test. Now be careful because you might just be like, oh, I'm using the z distribution. I need to do a z-test. Stop and look. You are doing proportions, okay? Your calculator programming needs to know if you have quantitative or qualitative data. Qualitative being exactly what we talked about at the beginning of the year. In this case, it's like, are you married or not? Yes or no answers are qualitative data. The programming needs to be correct for qualitative data. So you're going to do 0.62. This is why your X value is important. Okay, you need to plug in the number of successes, not p hat. And we're doing a less than test, and you can tell it to draw. And you can see here, we did everything correct. Now my Z is a little bit different, but that's usually because of some rounding or something like that. It takes into account a lot more things. The calculator is going to be a little bit more exact, but we end up getting the exact same answers that we did, and we actually have an exact p-value. Now remember, this E, okay, is the same as saying, this will be the final thing here, times 10 to the negative fourth. Which means if you have 1.0, you're going to take this decimal and move it to the left 2, 3, 4 times. Okay, so that's true that my p-value is less than 1/1000th because it's 1/10,000th. Okay, and so that's how you would use your calculator to find these answers here. I hope that that was very helpful for you for completing the homework. Each one of these questions has like several iterations of very similar things, and that is it.